Hi, if you are a civil engineering student or even if you are a working professional and since you had been a student at some point in time in your life, your professors or your seniors might have told you that you should read the IS code from start. I have heard this many times from my professors. I think that will be the same with most of the students. Many times you might have planned to read it from first close to the last but never completed this. Some of you might have done that, some of you might not have done that. So now let me tell you something really important. Reading is, yes, important, but at the same time, interpreting the code in the right way is even more important. Hi all, this is Premjit here from civilera.com, and today I'm going to discuss 5 important code provisions which are interesting to interpret. Before getting into the 5 clauses that I mentioned about interpretation, let me give you 3 different tips that will help you to interpret any clause in any code. First thing is that always read notes below the clauses. In many cases, the code clause will have notes and subnotes under the clauses. So when I explain some of the clauses which I mentioned, you can see in the code that notes and subnotes are present. So I will guide you through that when I explain the 5 clauses which I mentioned. Never miss to read them because that's going to be sometimes more important than the clause itself. The note. I can show you that. I'll be showing examples in the sections below. So please read the blog as well in addition to hearing this video. If you are referring to tables in codes, many times you will refer to tables in codes and the table will be coming from a clause. So please make it a point that you read the clause from which the table is coming. So there will always be a cross-reference from the table to the clause and from clause to the table. So you have to make it a point that you read both of these. Why I say this is, the clause will have something more to tell you about something really important. It's not that only the table or only the clause is important. And the last point is that always remember that reading some IS code provision needs a skill. It's not just reading that. Don't just assume you are right if you are even slightly confused. If you think that, okay, there is something more that I need to know about it, I think perhaps I am wrong. If you have that feeling in your mind, you should definitely discuss this. You should discuss with your peers. You should discuss with others. You should discuss with seniors and understand what it really means. So somebody who has already gone through that clause and somebody who has already used that code and clause for a long time may be in a position to help you out with a clear interpretation. So keep these 3 points in your mind whenever you are going to interpret a code provision. And I told you about 5 clauses that I'm going to discuss today, and the first one is from IS 875 part 2 and the clause number is 0.3.3. So you may be surprised sometimes to know that IS 875 part 2, where most of the engineers consider this as a reference code for live loads, has something very important hidden in that. So this clause is something like that. So if you read this, I will also take you through the code in a minute, but let's just read this particular clause. The buildings and structural systems shall provide such structural integrity that the hazards associated with progressive collapse, such as that due to local failure caused by severe overloads or abnormal loads not specifically covered therein, are reduced to a level consistent with good engineering practice. So this is completely confusing. It's a very long clause with no full stop and comma, and it might surprise you. It may be a lot of confusion for a beginner. So I'm going to interpret this for you. Let me also take the code and explain this to you. So this is the clause. You can read it again. It is exactly what I have written there. So it tells you that you have to do something for progressive collapse, but then it's not really clear. Many engineers interpret it like, okay, I understand this. You have to design and detail properly, and that detailing will take care of progressive collapse, because there is a word here that consistent with good engineering practice. So people tend to believe that, okay, if I have a good engineering practice, then I'm going to achieve progressive collapse control. That's the clause meaning. No, that's not the clause meaning. It's in fact making you responsible for progressive collapse. So what it means is that your scheme should be really good so that you have alternate load path in your building, and because of a great scheme that you have, because of a robust scheme that you have, your normal detailing or good engineering practice is going to bridge any failure of a key member, and that will allow an alternate load path, and your building is not going to completely collapse. So that is what the clause means, and it's making you responsible for that particular point. So I will explain this with a sketch so that it's clear to you. So what it really means is that in case if you have a building like this, and if you have a column each here, and if one of the column, let us consider that if this column is going to collapse, assume that this is going to be 6 meters. Due to any accident, if this column is removed, what happens? What happens is that this entire 6 meters will have to act as a cantilever in order to ensure that the building doesn't collapse. So it might be a little difficult for the building to cantilever like that. So this may not be a really great scheme. So what it means is that you need to ensure that you have one more column here, so that in an eventuality of this column getting failed, your building has some bridgeability. Maybe this can act as a cantilever and save your building from disproportionate collapse or a progressive collapse. So that's what the clause means. Same way, if you have a structure like this, and provided you have a excellent design here, and say in case if this beam fails, again the slab should not collapse, it should have some bridgeability. At least for the unfactored load, this should be able to span as a two-way slab like this. So you may have to tweak your detail, you may have to slightly adjust your curtailment, lapping location and all that, and ensure that you have bridgeability. So for example, if I clarify it really well, say for example, if you have this, and if you have detail with cut bars here, so you have one bar and one bar like this, and on the other side also you have something like this and this, you have cut the bar. What happens is that when this particular beam collapses, your slab may not be able to act as a two-way slab because you don't have continuity of rebars here. So to ensure that, you might have to ensure that the rebars are straight, it's not curtailed there or it's not staggered there. So planning this alternate load path is what the code makes you responsible. Now if you want to have a better understanding of that, I have a different video for this which I have cross-linked. So please ensure that if you are watching my YouTube video, please ensure that you read my blog as well. The link to the blog is in the description, so please read that, because you will get a link to another video, an earlier video, which is explaining this principle quite in depth. I don't want to repeat that here, so you have to refer the other YouTube video which will be referred from the blog. So please ensure you read the blog as well. So the next clause that I want to discuss is about effective length. So for discussing effective length also, let me take you to the IS 456 this time and take you to one of the clause here which talks about slender columns or short and long columns. So here you can see that based on your effective length by depth or effective length by width ratios, if it's more or less than 12, based on that you will decide if your column is slender or not, if it's short or long. So if it's more than 12, it's long column, and you have to calculate the slenderness moments and then add that to the frame moments for your column design. This is what you have been doing in your college and in your textbooks and in your practice everywhere. But then here there is a great difference in the understanding of what effective length is all about. So if you see here, it's very clear that you have LEX and LEY, which means that there is something in that. It's not your center to center height of the column, it's much more than that. How can you have two different heights in X and Y direction? So this is something which you should think about. And now once it is slender, then you perhaps go to this particular formula and then calculate your additional moments or slenderness moments in either direction. So this is what you have been doing in SP16 or in textbooks, or if you even use any of the software, this is perhaps the software also will do. But then what is this effective length? Many students and many engineers, even practicing engineers, take this particular value from table 28. So now here it says if you have both your top and bottom fixed, then you have a recommended length of 0.65 L, and if it's pinned you have something else. So now my question is, are you in fact pinning or fixing your joints, not the support? I'm talking about the column beam junctions in your analysis model. No, you are not doing that. You are leaving the stiffness to play. You are assuming that the software will develop the necessary fixity based on the stiffness. You are not assuming, you are considering that, and that's a right consideration, and the stiffness plays, and then you get your fixity and your inertia or your stiffness in the right way, and then get the load distributions. That's the right thing to do. You are not pinning or fixing the joints. Now when you are not doing that in the analysis, in design, how can you assume that to be fully fixed or fully pinned? So that's not really right. So if you come to the previous page of this in Annex E and then read here E3, it clearly tells that for normal usage, assuming idealized conditions, the effective length of the column in a given plane may be assessed on the basis of table 28. So here there are three ambiguities. One is that code says that it's for normal usage. Second thing is that it is for idealized conditions, and the third thing is that it is only an assessment. It's not a final thing that you can do. It only is a guideline. It's only to be used as a guideline, as an assessment. Okay, this is the way it's going to be, not that it is exact. So if you want more exact result, more exact effective length, you are not supposed to use that for normal usage. Perhaps this was when your code didn't want seismic to be considered. Maybe long back when only gravity was considered, this was a normal usage and idealized conditions. So for a very small building where you don't have the seismic to be looked into, but in India all the buildings has to be designed for seismic loads. So probably this cannot be used for any column design. Now what it says, the code says that if you look at another clause here which is related to the effective length, the code directs you to Annex E. So if you see here, in the absence of more exact analysis, the effective length of columns may be obtained as described in Annex E. So Annex E is the place where you should find your effective length. So coming back here to the provision, you can check here in Annex E that in the absence of more exact analysis. So exact analysis here means if you aren't doing P delta analysis, then you are required to do moment magnification or slenderness moment as per IS 456, and it says that if effective length should be based on various aspects as per figure 26. So you are required to calculate your sway index as per E2 here, and if your Q value is more than 0.04, then you have to consider your frames or floors as sway and then go to this table to get your effective length factor. Or if your Q value is less than 0.04, then you have to come here and then pick your effective length factor based on no sway condition. So this is very important, Q value calculations and how we can arrive at these graphs. So if you are using a software like Etabs, it will automatically do that. So I will guide you through that in a different video or in our training programs. But then currently I'm not taking you through the entire process, but then it is possible to assess this Q value and then get into the exact effective length factors rather than adopting things that are mentioned in table 28. So I advise you understand this entire stuff and then interpret it rightly and then do the design of columns based on sway or non-sway. So the next clause that I'm going to talk to you is about minimum eccentricity, and you can see it here. All columns shall be designed for a minimum eccentricity equal to unsupported length of column by 500 plus lateral dimension by 30, subject to a minimum of 20 millimeters. So you know all these. I'm assuming at least that you know this, and what I'm going to talk about is the last sentence here. Where biaxial bending is considered, it is sufficient to ensure that eccentricity exceeds the minimum about one axis at a time. So this is something which is very important to understand. All of you might be knowing about the first part, but I'm going to help you with the second part. This is quite interesting, and I have mentioned the story behind that, how I came to a conclusion and how I was guided to find this particular close out. So please read the blog in addition to what you are listening here in the video. I have mentioned the story behind that in my blog. So coming here, so assume that you have a column and a frame, and you have your load in the column as something like 1000, and say you have your mx, that is your major axis moment, as something like 90, and you have your MUY as, that's your minor axis moment, as something like 30. So I'm just assuming something here so that I can explain this. Now MUX means your major axis moment. This is going to be your MUX, and the other one is going to be your MUY if you have a frame action in both directions. Now assume that your minimum eccentricity moment due to the eccentricity in that direction is 100. I'm just writing a figure. It could be less, it could be more. I'm writing it as 100, and assume that in the other direction it is around 40. Now if you look at your SP16, or if you look at any of your textbooks, what you will see is that your final design forces are going to be 1000 for your PU, then your MUX is going to be maximum of this, so it is going to be 100, and then you will have something like 40. So this is your final design force. Slenderness moments are going to be added to this, but then I'm talking about frame moment being replaced by the higher eccentricity moment. So this is what you will find. But what this clause, the second clause, tells, and many engineers don't understand or interpret it rightly, is that the code is asking you to take only one eccentricity moment at a time, which means that code is asking you to consider only one eccentricity. That is, if you have a beam which is coming as eccentric in this direction, code is asking only to take that. If you have eccentricity, say this is the center of the column, and your beam CG is not coinciding with that, this is also not coinciding with that, then that's when you have a eccentricity moment in either direction. So code is asking that, probably because the chance of both coming at the same time is less, code is asking you to consider only one at a time, which means your first design becomes 1000, then your MUX is going to be 100, the more among the frame and the eccentricity moment, and the second MY only 30 needs to be taken. You need not take 40, because that's what code says, one at a time. So this one design you do, then second design would be 1000, and you have to take your 90, and your MUY has to be 40 here. So here you are taking the maximum among 30 and 40, and here you retained it to 90. So only one at a time. So 90 is retained, 30 is replaced by 40. Here 100 is replaced and 30 is retained. So two design, and whichever gives you the maximum steel, that is what you have to take. I'm not sure how many of us might have appreciated this fact and then complained that Etabs is giving a wrong design. So these are very important to understand and interpret in the right way. The next clause that I want to tell you is about a table 18 here, and you can see that there is a load combination 0.9 DL plus 1.5 wind load. So my whole point is that when you have a combination of 1.5 DL plus 1.5 EQ, what is the need of 0.9 DL plus 1.5 EQ? 0.9 is less than 1.5. So why do we need that particular combination is my question. And to understand this, you may have to go through my blog entirely and then write down the entire load combinations and then check it out. So if you do that exercise, you will be able to appreciate what I am talking about. And please also note that I have a different webinar on this particular topic, which I have cross-linked in the blog. So please read the blog as well and understand that, so that it's completely appreciated by you. So why do we need that? So that particular need is in fact mentioned in your notes here. This is why I told you, when you are reading table, always read the clauses associated with this. you can see that it's directing you to some clauses. Also note that there are nodes. So this is a node and you have a sub node here. So that sub node is coming from this 0.9 DL plus 1.5 wind load or earthquake. So why is it needed? There is a sub node here which says that this value is to be considered when stability against overturning or stress reversal is critical. Now, how is that becoming critical? What is that overturning? What is that stress reversal? I have mentioned it in a different video and I have directed you to that video in the blog. So please read the blog. And my last point is on torsion, and I have a separate blog for torsion as well here in my blog. Again, that's cross-referred in the blog. So please read the blog so that you get the video or the blog additional in that. So here I have completely mentioned what torsion means, and primarily what I want to tell you is that the code interpretation is very important, because even in that case, the code is asking you to release the torsion, which also is going to be equivalent to designing for torsion. So that's what I want to arrive at. The entire explanation is given in this particular blog. I will just show you the code provisions and the notes so that you understand how and why it is important to interpret. So everybody knows that 41 is the limit state of collapse torsion clause, and generally people come to this particular clause. So if you read here, design for torsion is nothing but increasing your shear by a empirical formula. So if this is your shear force, you are adding another value here based on the torsional amount and then increasing your shear. So what basically happens is, if 60 was your shear, now the new shear becomes 70 or 80 depending upon the magnitude of the torsion. So designing for torsion means increasing your shear just by a blind formula. Same way, increasing of moment. If your moment was 100, you are going to add another moment to that based on the torsional value. So designing for torsion means increasing your shear and increasing your moment. That's all. So if you design for an additional torsional value, means that you are enhancing your shear force and enhancing your moment. Now, what people generally miss to notice is that here when you come, there is a very important interpretation problem. However, for such indeterminate structure where torsion can be eliminated by releasing redundant restraints, no specific design for torsion is necessary, provided torsional stiffness is neglected in the calculation of internal forces. So this is what you need to interpret very properly. So what it means is that code is saying that if you are neglecting the torsional stiffness, which means release the torsional stiffness, then you don't have to design for torsion. Now, why is it that? Everything is explained in the blog, so please read the blog to understand that effectively. Finally, what I want to conclude on torsion is that in case of an equilibrium torsion, you have to design it as per the formula, and in case of a compatibility torsion, you design it as per the formula that I showed you, or you release the torsion. Both are going to be the same principle. Values will slightly differ. I again request you to read the blog so that you appreciate what this is all about. So you can also see the note here, which is a small text which also explains in a bit detailed way on what torsional release is. So it's very important that you interpret the clauses, notes and subnotes in the right way for your exact understanding. So I would like to conclude this video by once more telling you that code interpretation is a skill and you need to develop that skill. You may have to read the code many number of times and then connect it to the logic behind that particular provision. If you are confused at any point in time, you can contact your seniors or somebody who might be able to help you with that. In case if you want to discuss any of these clauses with me, you can feel free to connect me either through the blog comments or through the forum, or I have given a lot of links in the description and in the blog for initiating discussions on these kind of topics. So I once more request you to read the blog in addition to the video so that the understanding is complete and you get all the links to our forum and other contact options. So thank you for listening to this video and I hope you understood some of the concepts, and I hope you will get back to me in case if you have any confusion on these topics. So thank you once again.